particularly. It's been a really nice conference so far. Now it's the last day. And I'm really happy to have a chance to visit Korea. So what I want to do is not part of the toric topology canon, really, but I'll make some advertisement that the pieces that we'll see in here are really things that you'll find friendly and I hope appealing objects. So this is part of some joint work with Alex Suciu and Sergei Uzvinsky. Alex mentioned a bit of it. Yeah, louder? Okay, sure. I don't want to use the microphone, but I'm capable of talking really loudly. So tell me if I start slipping. And I want to talk about a particular theorem. Oh, pardon my technique. I find if I write Beamer slides, it changes what I say.
Which tech font is that?
It's a very rare font. I'll let you have it, though, if you pay me enough money.
It's easier to read. I like this.
Oh, thank you. So,
great talk.
So I'm going to recall duality groups and some setup to talk about cohomological vanishing properties for groups and spaces. And I'll give some examples and then try to prove a theorem that I'm advertising just to have a particular focus. Oh, and here are some co-authors. I'm not sure if, has Alex got that lovely green hat back? It had a little misadventure at the conference excursion. Yes, all right. And poor Sergei, he looks sad because he's not here. Okay, so Alex mentioned this definition, but it goes back to Bieri and Ekman. It's quite classical. I should say one thing that sets me a little bit in the corner here is that my spaces have a non-trivial fundamental group, and I mean other than the torus. So we have to put up with that. My group cohomology with group ring coefficients is the same as the cohomology of a space with group ring coefficients when the space is a k pi 1. And a group's a duality group if, well, FP, assume it's a fundamental group of a finite type CW complex. That's close enough. If there's a single non-vanishing cohomology group with group ring coefficients. And you'd wonder why this. It generalizes Poincare duality in some sense. Wedges of spheres of the same dimension, wedges of circles are Poincare or duality spaces, but not manifolds, so not possessing Poincare duality. And there's a large class of groups for which this property is known. It has something to do with Cohen-Macauliness in some homological algebra sense, which we'll see later. So the spaces that I'm motivated by are configuration spaces. An ordered configuration space is just informally the set of all points in X, endpoints in X, which are distinct and not equal to each other. Some particularly, motivated ones would be the configuration of endpoints in the complex plane. The fundamental group of that is the pure Braid group. You can think about unordered points as well by letting the symmetric group act freely on the configuration space. Then the fundamental group of the quotient is the classical Braid group. I won't mention these because they're irrelevant to my talk, but the theorem I'll state will apply to ordinary as well as pure Braid groups. If I take a 2 torus, E, I'll call it an elliptic curve because it's nicer, then the fundamental group of that configuration space is the so-called pure elliptic Braid group. It's an elliptic generalization. One way to think about it is to imagine some kind of braiding of points, each of which lives in a 2 torus. Craig Squire showed in '94 that the pure Braid group is a duality group. And this is a property that's inherited by the Braid group because that action by the symmetric group gives a finite cover, a regular cover. And the duality property is inherited by things like products and covers. If I think about the universal cover of the elliptic curve itself, then I can extend it to a Cartesian product of elliptic curves. That's the ambient space for this configuration space of points in an elliptic curve. And a theorem due to Miguel Hico-Tencatl from his thesis, which appears in a joint paper with Fred Cohen in 2002, states that the restriction of the universal cover of the n copies of the elliptic curve to the configuration space is itself a covering map. And the space above, the orbit configuration space they called it, is a complement of an infinite collection of hyperplanes translated by the lattice given by 1 and tau in each coordinate. So a hopeless task is to draw an infinite hyperplane arrangement. And of course, I can't even draw a very good one because it's intrinsically complex, right? It's got a parameter 1 and tau, so there are translations in 2 different directions. This is one of these sort of doubly affine constructions. So I want to complete this introduction by saying that the main point of application of what I will tell you is that this fundamental group of the configuration space of points in the elliptic curve, ordered or unordered, is also a duality group. And it's part of the larger program to say what conditions allow us to show cohomological vanishing for modules over the fundamental group in this way. And what is a suitable space? Well, I guess suitable spaces for us turn out to be spaces that seem to include high-rank subtori, or high-rank tori, for which the induced map in the fundamental group is injective. So groups which contain large free abelian subgroups, and more. So let's find out. Here's a combinatorial machine which I'll mention, which I hope is not off-putting, but it's a little bit technical. But if I imagine something like this configuration space, a nice ambient space with some submanifolds cut out, then I'll set up some formalism to generalize these sorts of things by looking at the stratification poset of submanifolds in a larger manifold. And I'll consider open covers with some nice properties so that I think the picture shows what I want. I would like my open sets in the cover to intersect the submanifolds, whatever they are, nicely, so that there's a unique point which is minimal with respect to inclusion in the stratification poset in each open set. So that's to say I don't want sort of peanut-shaped open sets that touch these components in more than one place. And if I have that, then I get a map from the nerve of the cover to my stratification poset. And you should try not to imagine covers where the open sets are contractible, good covers. These are not good covers, and this is somehow where the magic will come from. Oops.
They must be the sizes of Canadian coins, aren't they, those circles?
Yeah, at least the big ones. Okay, so a technical definition, a combinatorial cover is a countable cover of a space together with a finite poset. Some conditions on a map from the nerve to the poset that ensure that things are nice in some way. So if I have collections of open sets in the nerve, one with more open sets than the other, then this map, if it sends my 2 collections to the same point in the poset, I would like the induced restriction map on the space level to be a homotopy equivalence. And some other condition that if I have comparable collections in the nerve, number 2, which actually index the same intersection set theoretically, then the image in the poset is the same. And then finally, there's some map to the integers which induces some grading, which we'll use to make a spectral sequence. And we've heard about it before. A couple of people have worked with a Meyer-Via-Torus type spectral sequence. I guess there are endless variations on this construction. So with this, if we have one of these combinatorial covers, pardon me for calling it weak. I used to use that word and it should be deleted. Then if I had a local system, which I have to think of as a locally constant sheaf on my ambient space, then I can form some kind of spectral sequence indexed by, say, this stratification poset, where the E2 page splits into pieces, where I have cohomology of some pairs. These are, let's see, I think my next slide explains it, subcomplexes of the nerve, so something more or less combinatorial, with some cohomology coefficients these cohomology coefficients were coming from small open sets in the cover. Whoops. Right. So these coefficients are a little bit dangerous because I leave the world of local systems. I have to work with constructible sheaves because I've got something which is a local system somewhere but zero elsewhere. That's what this relative construction means. And I know Tony's dying to say, this guy doesn't even know what he's written on his own slides. And it's true. I hope that says what I think it says and nothing more embarrassing.
Like a robotic sign for show danger.
Yeah, exactly, right, yes. So we have to watch out for that. Sometimes these coefficients are trivial coefficients, which helps a lot. Okay, right, so if I have this collection of submanifolds and an ambient manifold with some mild condition on how they intersect, then I get such a spectral sequence where my pairs come from, strata in the collection of submanifolds, where I consider one stratum relative to the stuff inside of it. And then perhaps the picture shows, you know, if I have those 4 lines inside my manifold Y, and I pick on the term X being the red one, then what's inside are these little blue dots, and I've got something that looks like the same thing, an arrangement of submanifolds inside a smaller manifold. And the coefficients are valued in the cohomology of those little yellow balls, local contributions. So if we consider a construction with polyhedral products, we can make right-angled Artin groups, as probably everybody knows in here. The right-angled Artin group is the fundamental group of the Charney-Davis complex, which is one of these constructions using the pair of a circle and a point. The group itself is presented using relations that come from the one skeleton of the simplicial complex. And without saying exactly how that goes, because you already know it, most likely, the classifying space for this group is a k pi 1 if the complex K is a flag complex. And we can make one of these combinatorial covers using the subtori themselves as the well, actually, I have to thicken them a little bit to make open sets instead of closed sets, but that's not a problem inside this torus. So I will get a combinatorial cover indexed by the faces of the simplicial complex K. And so here we have, you know, a free group F2 inside the 2 torus. So using the spectral sequence, one can prove that if the complex K is Cohen-Macaulay, and I think Anton Eisenberg defined that yesterday. It's a condition on the links inside the simplicial complex. And the module, the local system, the module over the right-angled Artin group A is also Cohen-Macaulay in the algebraic sense over the maximal abelian subgroups. Then we get the sort of vanishing property from our original question. And in particular, if this is a k pi 1, then that could be cohomology of the group. And the coefficient module, if I take the group ring, happily it satisfies this Cohen-Macaulay condition over all maximal abelian subgroups for not very difficult reasons. So then we obtain this sort of vanishing, and with another thing I'm not telling you about, that the non-zero cohomology group is torsion-free, then we can recover the result of Jensen and Meyer. The right-angled Artin group is a duality group when the underlying simplicial complex is Cohen-Macaulay. But of course, there are other examples, including the group ring of the abelianization of the fundamental group, which Alex talked about at the beginning of the conference. And then roughly speaking, you know, if you play with spectral sequences, you'll recognize how this would go. I had this E2 term, which had some nice description in terms of some pairs of relative strata And then I had cohomology from a local contribution, which in this case is the cohomology of a torus. So that's all pretty easy. My coefficients, I can decide exactly what conditions to impose on the module to make this vanish. And then the combinatorial condition makes this part vanish. So then I can get an E2 page which is concentrated on a single anti-diagonal. So it's quite straightforward. Another family of examples comes from arrangements of hyperplanes. Let's start with hyperplanes in C to the n, pardon my squishy writing, linear hyperplanes through the origin, such as configuration spaces. That's given by the hyperplanes normal to the type A root system, define the configuration space of endpoints in C. So that's a good one. There are others. If I make sure my hyperplanes pass through the origin, then there's a diagonal C star action. I can take the quotient, and that's a better thing because now my ambient space Pn is compact. Even better, I could consider an ambient space which is compact and gives me nice intersections of strata on the boundary. So, if I use the appropriate blow-up, usually one talks about the De Concini-Procesi wonderful compactification. There are other ways to say this, but it's not too hard to find an ambient space for which the arrangement complement has on the boundary components which intersect locally like coordinate hyperplanes. So this is friendly to my spectral sequence because I will cover it, and then my local contributions will be complements of things that look like coordinate hyperplanes. So my local neighborhoods will be homotopic to tori. And those were the ones where I had to control some property of the coefficients. So let's see. It turns out also that arrangement fundamental groups contain relatively large free abelian subgroups. I guess I just said that in a sense. If you see that neighborhood which looks like a torus that lives in the arrangement complement, if you knew that the inclusion induced an injection in the fundamental group, then you would see a large free abelian subgroup. And it turns out that's true. So if the cohomology vanishes for these free abelian subgroups for my coefficient module when I restrict, then it turns out it does so for the entire arrangement complement. And there's a long literature of vanishing results for local systems on hyperplane complements, beginning with a result of Kono, who proved the same result with the appropriate hypotheses when A is a finite dimensional representation over a field. And then the condition becomes much easier because I don't need to check abelian subgroups larger than Z. So well, I'm omitting a bunch of literature. I'm citing a paper that I probably shouldn't cite. Rather, there's some work of Dimka which gives another criterion for cohomological vanishing. Again, in the case of finite dimensional representations, when A is the group ring, Davis, Januszkiewicz, Leary, and Oken showed that the hyperplane complement is a duality space. And you will wonder why I'm saying we should consider representations which are not finite dimensional. Well, the group algebra of an infinite group is not a finite dimensional representation. So, of course, if we wish to speak about duality groups, then we need to admit local systems which are not finite dimensional over the base field or over the integers, if that makes sense. So, again, just a quick look at how this program works here. I'm pulling back my previous slide. If I have arrangements of submanifolds and an ambient manifold, I have some spectral sequence that's supposed to help me out. In this case, that pair consists of an ambient space which is compact and a complement which is a Stein manifold. And the good news about a Stein manifold is it already comes with its own cohomological vanishing property. these are n-dimensional complex manifolds which are homotopic to half-dimensional CW complexes. So there can be no cohomology above degree n. And I guess we could also call it the Artin vanishing theorem in the analytic case. But if I combine that together with the ambient space being compact, it's tempting to write a little, yeah, I think I won't do it. But so if you were teaching algebraic topology, you'd remind your students that you should replace that pair by the complement with compact support. And then since I've got these coefficients, I should use some kind of Poincare duality to flip the over to homology. But actually what you really want with these sheaves is to use Verdier duality and then be a little bit careful about how you dualize. But if you do that, and then you realize that the output, my hyperplane complement, was also a Stein manifold, then I get some zeros below the diagonal from the one side, and then of course there can be nothing above dimension n minus 1 because we know what the answer is in some sense. So there's a squeeze, and we get we get this result. Okay.
Is it necessary to compute differentials in that spectral sequence?
No, happily not, because it's not a very good spectral sequence from the point of view of differentials. The way we make it comes down to all that technical stuff meant that we understand the E1 page really well by filtering a check complex. And then we understand the differential intimately there, but then once we get to E2, it's we just hope that things are zero. So then to get to the point in the title, we could also consider elliptic arrangements. I'm not sure if you can call them hyperplanes if they live in products of elliptic curves. But as we saw with the configuration spaces, these complex codimension 1 abelian subvarieties of e to the n lift to infinite translates of hyperplanes in the universal cover. So these were considered in particular by Kristen Bibby in a recent thesis at the University of Oregon. And she computed the cohomology ring for the complements quite explicitly, generalizing the description of the cohomology ring of the configuration space of points in the torus, which is known sort of implicitly from the Cohen-Taylor spectral sequence and more explicitly from the Totaro spectral sequence. But in terms of an actual presentation, you should look at Bibby's paper. Okay, right. So we can understand these though because they follow the same program. The so-called elliptic hyperplanes intersect in neighborhoods that look like ordinary affine hyperplanes if you consider the tangent space. And our motivational example is this points in the elliptic curve. I make a little joke. How much time do we have, Matthias?
7 minutes.
Right, yeah. So yeah, this is just to compliment my co-author, Alex. I don't really have 24 more slides. Actually, I'm almost done. So if we, if we have such an arrangement, then we need to attach some more adjectives to make sure that the components intersect strictly at the identity and don't contain an entire elliptic curve or something bigger. That's essential. And unimodular means that they don't intersect along torsion groups which are bigger than the trivial group. You can rephrase this by writing down these subgroups as kernels of group homomorphisms from n copies of an elliptic curve to an elliptic curve, taking kernels which are given really by integer vectors. Weights, right? And then the associated matrix is supposed to be unimodular. That controls this unimodularity behavior. And so the conditions on the coefficients, now I can say rather briefly, I need to check that I have the cohomological vanishing except in the expected dimension on the local hyperplane arrangements that appear where these components meet. So to say it fully takes more ink, but I hope that's enough to give you the general idea that I'm going to bootstrap from the previous theorem to get a vanishing result for these guys. And then the point is that these hypotheses are understood enough so that, for example, the group ring of the pure elliptic braid group satisfies them. It's got this Cohen-Macauliness over all finite abelian subgroups of all local subarrangements or whatever. It comes from being a free module over group rings of subgroups, basically. So then we find that the pure elliptic braid group is indeed a duality group for n greater than or equal to 1. There's a little bit of a technicality, because if you're fast, you might notice that whatever I said about essential doesn't include these configuration spaces. In fact, what you have to do is notice if you project onto the first factor, then you get an entire E, and this is split. So I can actually write down a fibration where the, did I get it backwards, Alex?
Isn't that n minus 1?
Oh, n minus 1, yeah, sorry, yeah, right. Right, so if you look at the fiber by fixing the first coordinate, then what remains is a configuration of n minus 1 points in a punctured torus. And then this is a trivial fibration, so this is actually a product. And then duality behaves well with respect to products. So the elliptic curve, being a torus, has definitely got all the duality you could want. And so then it remains to prove the result for this. And then that actually turns out to be one of these guys that fits the hypotheses. So let's see. I think that's it. Thanks.